right, so there we go. It's recording. So we're going to wrap up chapter 7 and move on to chapter 9 today, hopefully. And the most important part of chapter 7 is, which we didn't get to yet, is the spectral decomposition theorem for infinite dimensional Hilbert spaces. It's, the eigenvalues and eigenvectors theorem for, operators, but in infinite dimensions. And it looks a little bit different than the finite dimensional case. But before we get to that, again, I wanted to go back to this example just shortly. I sort of ran out of time, but there was this example of, functions in our space L2 square integrable functions living on the interval 0 to 1. And we have this operator A naught, which was minus I times the derivative with respect to x, acting on functions psi of x such that psi of 0, psi of 1 is equal to 0. So that's the domain of A naught. It's basically the domain of A naught is such that when A naught acts on the function, right, it has to give you something that's square integrable, because that's the space we're in, square integrable functions. And so the domain is everything that when you act with the derivative, that the derivative of the function is also square integrable, and also as part of the definition of the operator, you specify the boundary condition. So in this case, it's this boundary condition. And the only thing I wanted to kind of mention about this is if you have a dagger doesn't necessarily have the same domain as A naught. It might be able to act on a larger space of functions. And that was the last thing I kind of wanted to mention. Last time I sort of didn't get around to it, but the basic idea here is, let me write this write it as a complex conjugate. So if we consider the following, A naught dagger, right, acting on chi phi, inner product, then this thing is, of course, this is acting on the bra, so you get a plus I, you get an I, and then an integral from 0 to 1 dx of chi prime x complex conjugate phi of x dx. That's just the definition of the inner product. And then we can do integration by parts. So that gives you the product of the two functions evaluated between 0 and 1, and then you get minus I dx with the derivative flipped. And of course, this is on the quiz, but so this is starred, and now the derivative is on the phi function. And this right here, as long as phi satisfies this boundary condition that it vanishes on the interval, then we can ignore on the boundary of the interval, then we can ignore this piece, and this just becomes chi A phi. Because, if we say A acting on phi, we mean by that phi satisfies the boundary condition. Because if we write it this way, this means that, phi is in the domain of A naught, I guess. And you see this strange thing happens, that this chi back here, this chi, it can have any boundary condition. Because if we do this manipulation, we see that this is equal to that anyway, so long as phi has the right boundary condition. And it must, if we write, this, equal to that, then we mean that, you know, A naught is acting on something in the domain. Operators always have to act on something inside their domain. So if we write this, we mean phi has the right boundary condition, but chi doesn't have to. And so this is, in this sense, we say that A naught, right, is kind of like a subset of A naught dagger, because A naught dagger can act on a larger space of functions. We can extend the definition of the dagger to be able to act on any function with any boundary condition. And so that's kind of an important point, is that in infinite dimensions, you have to be very careful about the domain of an operator. It's the space of vectors that it acts on, such that you get back out something that's in the Hilbert space. And it's not even the case always that when you take the Hermitian conjugate that you get the same domain. Often the Hermitian conjugate can act on a bigger set of vectors in your Hilbert space. And again, this brings me to this notion that when we write something like A is equal to A dagger, what we mean by this, and you know, this I would call it a self-adjoint operator, is that the domains of these guys are the same, that the domain of A is equal to the domain of A dagger. It acts on the same set of vectors. Doesn't have to be the whole Hilbert space, by the way. It's something I didn't quite emphasize properly last time. But that doesn't have to be the case. It could be that A dagger acts on a bigger set of vectors in your Hilbert space. And then you could write, like in this example, that A is kind of a subset of A naught dagger, that they're equal, that these guys are equal on the domain of A, equal on the domain of A, but, you know, the domain of A dagger can be larger. Can A dagger connect on more things? And this comes up frequently when we have something like, you know, the X and P commutator, which we say is, you know, IH bar identity. Don't really mean this acts on all of the vectors in your space. This does not. This acts on a subset of functions, say. And so we write like this, right? That they're only equal on the domain of this guy, on the domain of the smaller guy. This is a smaller domain. So it's something important to keep in mind. That's a very crucial feature of these infinite dimensional cases. And in the notes, I give an example of how you can extend the definition of A naught such that, you know, A naught is equal to A naught dagger. And basically what you can do is, instead of A naught, you define a new operator, AC, which is, again, it's the same thing. It's minus I times the derivative, but now you have a different boundary condition. You say that phi 1 is equal to some constant C times phi 0. And you can also set the magnitude of C, some complex number, you know, with magnitude 1. This, if you work it out, you'll find that AC dagger has the same domain as AC. This has to act on the same kind of functions with these boundary conditions. You're no longer free to choose any arbitrary boundary condition. And in this case, you can show rigorously that, you know, AC is equal to its Hermitian conjugate, because these have the same domain. Okay. So you can read the notes for that. It's not so important, but it's good to sort of keep this in mind, right? It's and you know, we call AC. You can call it a kind of it's an extension of A naught. Meaning, you know, these functions, this includes, the boundary condition where they're both equal to 0. That's like part of this. That includes functions like that, right? Because that's the solution to this boundary condition too, where these are just both equal to 0. So this is a more general boundary condition, right? And so in that sense, AC is an extension of A naught because the domain of AC is, bigger, contains the domain of A naught, right? And you often do this kind of thing as you extend the definition of an operator by, say, making a more general boundary condition, such that you can get a true self-adjoint operator where it's equal, for instance, to its Hermitian conjugate on the entire domain, because you can show that the domain of the dagger now is the same as the domain of the operator. So it's a subtlety, not particularly important, I would say, in terms of what we're going to work on, the examples, but it's important to keep in mind as a feature of infinite dimensional Hilbert spaces. And again, when I say that, maybe you can imagine in your head that I'm talking about the space of possible wave functions, say, you learned about in undergrad quantum. Any questions about that, the domain issue?
I'm just a little confused about the notation that you used here in the blue ink at the bottom. A naught is a subset of A naught dagger. Did you actually mean D A naught is a subset of D A naught dagger?
Yeah, it's a shorthand. What I mean by this is if I ever write A0 is equal to A0 dagger, say, I don't, by this, I'm kind of implying that these two guys act on the same space of, they have the same domain, that if I have some psi, that this can act on it, and, this guy can act on it, and you get the same thing. But maybe they have different domains, so not all psi's belong in both domains, right? And only some psi's I can act with A. So in that case, instead of an equal sign, I put a little hook here. And so, yeah, it's the same as the subset symbol, but it's just shorthand, meaning that these are equal, but only, on the domain of this guy. And it also means that, the domain of this guy is contained within the domain of this guy. So,
okay.
So it's kind of the same thing. It's just a shorthand notation.
Right.
But yeah, you're right. It's a little bit confusing because this is a set of vectors, right? And this is an operator.
Yeah.
But right. This is something important to keep in mind when thinking about operators. And we'll rapidly transition to like thinking of operators just as like derivatives, right? It's important to keep in mind that every operator comes along with a particular domain. It doesn't necessarily act on all functions. It only acts on a certain subset of functions, and it's that subset for which, when we act on that function, we still get an element of our Hilbert space. And in the case of functional spaces, it means that when you act with the operator, you still get something that's in the that's still square integrable. And beyond that, you can have the domain include boundary conditions on the function too. So yeah, it's just, whenever you see an operator, you should think to yourself, well, what's the domain of this operator? What sort of functions does it actually act on? That's the idea. Okay, great. More questions. I will very rapidly drop this notation of subset because it's almost never used in physics books, but this is pretty important mathematics, I think. So okay, now for the meat of it, we're going to talk about spectral decomposition. And this is, eigenvectors and eigenvalues for infinite operators. But it's confusing how this would work. So say we looked at our example, you know, we have this example of minus I ddx, right? What would that eigenvalue equation look like? I mean, we know that it's basically like this, right? You know, we have to have some eigenvalue. That's what that eigenvalue equation would look like. And if we work this out, you know, this is acting on some function, should be equal to a constant times that same function. And this is solved by, you know, phi of a, we'll put little a naughts, I guess, for the eigenvalue. This is solved by, put little a naughts, I guess, to label the eigenvalue if we want. This is solved by the following, right? It's solved by a constant e to the I a naught x. That's the solution of this differential equation. This is not square integrable in the real line, for instance. If you know you let x range from minus infinity to infinity, then that's not a square integrable function because you just get the constant c squared. That's bad. And sometimes there's not even a solution. For instance, here's another operator, just x. Then you would have x, you know, times some psi of x is equal to some eigenvalue, right, times psi of x. This doesn't even have a solution. So thinking about the eigenvalue equation like this is not a good idea. We have to generalize it a little bit. And the way we generalize, so this is kind of, you know, not a good way to do things. You want to generalize the idea of an eigenvalue equation. And the way you do it is you take a complex number z times the identity, and you subtract off the operator of interest. And now this you treat as an operator which acts on a phi. And you ask what this does. You think about this operator itself, right? This is some operator. And you can ask about its domain. And you see all this is doing is it's taking this equation, right, and rewriting it such that, you know, you push everything over onto the left. And what we know what happens is these z's, if z is an eigenvalue, right, then what should we get? Well, we should get that, you know, this operator z identity minus a, it should be singular, right? Because in the sense that whenever it acts on any phi, right, if it's a true eigenvalue, then when it acts on this phi, the eigenvector, it should just spit out 0, which is a singular thing. So there are two cases, right? It's for certain values of z, you'll get a singular operator. And for other values of z, you get just a regular operator, which just spits back out, you know, some chi when you act with it. So z can have two different kinds of, there's two different cases for z. It's either a regular value, and then we can just invert the operator. or it's a singular value. And then, you know, the inverse of this operator is not defined. And it's the singular values which form the spectrum of, you know, A. We say that A has a spectrum of eigenvalues, and it's the and Z, you know, these singular values, they can have discrete values, they can be particular, you know, values of Z, or they could be like a whole range of Z's could be singular. And in general, you know, Z is a complex number. So
could you repeat that? What's the difference between regular value and singular value?
okay, so if Z is a regular value, then this inverse is defined. And what it means is that Z acting on any phi gives you another vector chi, you know, that's in the Hilbert space. And moreover, we can think about the image. So if Z is a regular value, then if you take all phi's in your Hilbert space, right, and if you act with them by this operator Z identity minus A, then you'll get back out the whole Hilbert space. So you can say that the image of Zi minus A, the image meaning the set of vectors that you get when you act with all of the, when you act on all of the vectors in your Hilbert space, the image of this operator is the entire Hilbert space if Z is regular. All right. Otherwise, it's singular. Otherwise, any other case, right? Z minus A will, so otherwise, I mean, what will happen really? If Z is a singular value, then it'll map some vectors, in particular the eigenvectors, right, to 0. And in that case, you can't define the inverse of this operator. And we say that Z is singular. So either this operator behaves nicely on all vectors of your Hilbert space, right? And that's what it means when Z is a regular value, meaning you put in any vector, it spits back out another vector, and you cover the whole space. And that means you can invert this operator, right? You can write any vector phi as, you know, the inverse of this operator acting on some chi. We can only do that for a regular value. If we have a singular value, we know that there'll be effectively some eigenvectors, right? Where if we act with this operator, instead of getting another sensible vector, we get just 0, the null vector. And so that would be a singular value for Z. It'd be a value for which, you know, this thing is not defined because it won't be defined on the eigenvectors. We won't be able to act on those because this operator acting on the eigenvectors will just give you 0. Does that make sense?
Yes, thank you.
So yeah, the idea is you pick a Z and then you ask, is this operator well behaved on all of the values of on all the vectors in the Hilbert space? Does it give you does it map out the whole space? You know, so you can think about maybe acting only on normalized vectors or something like that. And then you can ask, does it ever give you 0 basically when you act on all of the vectors? And if the answer is no, then it's a regular value. But if it sometimes gives you 0, like it would for an eigenvector, then you know that that value of z is bad because it has some associated eigenvectors with it. That's basically the way that I just think about it. And so then that's a singular value. And so then it's part of the spectrum. So a spectrum, meaning spectrum, which is equal to the set of eigenvalues, it's equal to the set of singular values of z for the operator zi minus a. So this is, so the spectrum of A, it's a set of eigenvalues, but they're not really eigenvalues because we're not solving the eigenvalue equation. What we're actually doing is we're studying this operator and seeing what it does on our Hilbert space. And if it ever gives us some zeros when it acts on all the vectors, then we know that something's wrong with that z, it's singular. And so then, it's not wrong, but it's one of the eigenvalues, you can say. And this means that, instead of taking a matrix, and diagonalizing it and so on, and getting some eigenvalues, lambda 1, lambda 2, and so on, what can happen is that z could have discrete sets of singular points. So, z, if, we have it for the finite dimensional case, those singular values of z would just be the eigenvalues, lambda 0, lambda 1, lambda 2, and so on. But z could also have a continuous portion. There could be a continuous set, like a range of z's, like z's between 1 and 2. Those could also be singular values, and those are also part of the spectrum. And then you don't necessarily have the kind of eigenvalue equation that we're used to up here that I circled in the black. For continuous values of z that are singular, it's not really it's not really appropriate to think about it that way. So this is the real way to think about it. And so what about these continuous values of z? For those, in physics, so in mathematics, it doesn't make any sense really to think about the continuous values of z as satisfying a eigenvector equation. So again, this only makes sense for discrete singular values. But we can extend this eigenvalue equation to include continuous singular values. And we do this by introducing things called pseudoeigenvectors. And these are not part of the Hilbert space, but they do satisfy they do satisfy a kind of eigenvalue equation, right? So let's do an example of what this means. How about this x operator that measures the position of something? Then, of course, we saw that we wanted an equation that, satisfies this kind of thing. So this is the operator acting on the function, which gives you x times the function, and here is the eigenvalue equation. And so the solution to this, the eigenvalues, the eigenvector, the pseudo-eigenvector, is a delta function, x minus a. Right, this satisfies this equation, right? Because this is a direct delta function. Hopefully you've seen it at some point. This function is 0 everywhere except where its argument is equal to 0, where it blows up, right? So, delta x, you can think about it as a limiting function. It's a distribution. It's 0 everywhere except at 0 where it's, blows up. And it blows up in such a way that if you integrate across any small region around the origin, that you always get back out 1. So it always, the area under the curve is always 1, but it's somehow infinitely peaked at 0. And so look at this. This makes a lot of sense, right? This is going to be 0 everywhere, right? Except where x is equal to a. And so then this equation works, right? When x is equal to a, you'll just get a here, and so this is the appropriate thing, right? And remember, we also had our operator a minus I ddx kind of thing, and we had this kind of eigenvalue equation, which looked like this, and the solutions to that, would be e to the minus IAX. Or plus, I guess. Yeah. So what about, and these guys, are also, we can think of them as kind of pseudo eigenvectors. And they're pseudo because neither the delta function nor this oscillating thing is going to be in our Hilbert space typically. It's not going to be, because it won't be square integrable, or it'll be typically some very badly behaved function. So this is all fine because these pseudo eigenvectors, they can still be, in a sense, orthonormal, except the orthonormality condition is a little bit different. So say we had one of these phi a functions, right, labeled by this a. Let's normalize it a little bit and just look at these functions like this, right? Square root of 2 pi. Let's take 2 of them, okay, and compute their inner product for 2 different values of the continuous eigenvalue. So again, this is, the a is the continuous eigenvalue. And if we were to compute that, what do we get? You get a 1 over 2 pi integral from minus infinity to infinity. Let's say this is in L2R, which is where we do most of our work, is square integrable functions on the real line. Is there a question? No? Okay, so let's explore this inner product. If we had discrete eigenvalues, we know that for the discrete ones, if we had 2 different so say we had 2 different eigenvectors, group A, and then maybe some other one B, with some other eigenvalue. We know that the spectrum, for a finite matrix, finite dimensional matrix, the eigenvectors form an orthonormal basis where n dotted into m would always give you either a 0 or a 1 if they're the same vector. So we're just trying to see what does that even look like when you have a continuous portion of the spectrum. But that's kind of what we're doing here, just exploring. So in this case, we're trying this funny eigenvalue equation where our operator is this derivative, and we're looking at all the possible eigenvalues of the derivative operator, which, you know, in this case is some A. So let's look at two of these guys, two different eigenvectors corresponding to two different eigenvalues, A and B. What do we find? Again, we get 1 over 2 pi dx. Here we get e to the minus I ax, and here we get e to the plus I bx. And what is this? Maybe you'll learn in math methods, but this is a Fourier decomposition, basically, of the delta function. This, evaluating this integral, so what does this give you? Is again 1 over 2 pi minus infinity to infinity dx e to the I b minus a x, right? So this is a Fourier transform of just 1. And this is a delta function, as it turns out. This gives you a direct delta function, and maybe a little more common notation is putting a minus sign here, and it's a minus b. Just rewrite it that way. This gives you a delta function of a minus b. That's just the property of the delta function. This is what the Fourier transform would be. And so that's a kind of general thing. We can also look at, you know, so that's these guys. We can also look at the delta functions, which are also pseudo-eigenvectors. Maybe I'll put these in green or something. Let's look at these guys. We can look at, you know, chi of A as these delta functions, x minus A, right? Let's look at two of these guys, chi A and chi B. What's the inner product of those guys? Well, it's the integral from minus infinity to infinity dx delta. This guy is x minus A. The delta function is just a real function. You know, dagger is complex conjugate is just the same thing again, times delta function centered at B. This this is going to be, you know, 0 everywhere except for the place where both of these are 0. And that only happens if A is equal to B. So we can work out that this object has to be the same as the delta function A minus B. So you see both these guys and these guys, they kind of have something that kind of morally looks like the orthonormality condition, which, you know, we know it's 0 or 1. Here, it's also kind of 0 or 1, except it's either 0 or infinity. And it's because instead of having a discrete index labeling, you know, the eigenvalues, you know, like first, second, third eigenvalue, now we have a continuous spectrum, right, of eigenvalues. And so the notion of orthonormality is different. There's two major differences. First is that, you know, the equivalent of the eigenvectors, they're not even in the Hilbert space. They're like very singular functions, either these oscillatory exponentials or, you know, delta functions. Those are the two main examples. And orthonormality is different. When we dot two of the eigenvectors, pseudo-eigenvectors, into each other, we don't either get 0 or 1 like we did before. We get a delta function where the inner product is 0 everywhere except where the two continuous values are equal to each other, and then you get, you know, basically infinity, but in a direct delta sense. So that's kind of our little exploration, right, using these examples that we looked at. Again, the two major examples, just to summarize here, the two major examples you would want to look at for continuous eigenvalues are, you know, this guy, this eigenvalue equation and this guy. And these guys have solutions, you know, these are the delta function solutions, and these guys have these complex exponentials as solutions. And neither of these, if you're thinking about the space L2R, neither of these are going to be in that space, because the delta function is really poorly behaved. You take the magnitude of the delta function squared and try to integrate it. It's going to be very bad news. It's going to give you infinity. And this is also not square integrable on the real line, because, you know, the magnitude of that exponential is just 1. So you're trying to integrate 1 from minus infinity to infinity. So that's bad too. They're both bad. They're both not in our Hilbert space. But if we extend the notion of this eigenvalue equation to include solutions which may be outside of the Hilbert space, then we can extend the notion of you know, eigenvalue and eigenvector in this way to include a continuous portion. So that's quite important. And I'm going to now state, you know, the theorem. Just the whole thing in one go. Now we've done this kind of exploration, and I won't prove this theorem. We just kind of explored it a little bit, but I'm not going to prove it. But any questions though about this little exploration? No? Okay. So again, the spectral decomposition theorem. So we're gonna, if this is for, well, we're gonna just state it for Hermitian, but we really mean self-adjoint operators A. And it also includes the unitary operators. It's similar as the finite dimensional case that, you know, it includes the projectors. So maybe I should put or sensible operators A. I don't actually know the exact criterion you need to get the spectral decomposition theorem, but it includes certainly the observables, which we will be worried about, like position, momentum, but it also includes other things like unitary operators. So it's the same as a finite dimensional case, except now you're going to have 3 different cases. So case 1, there's a discrete spectrum, right? And with eigenvalues a sub n, with n is equal to 1, 2, and so on, go up to any value. And then we have the eigenvalue equation like this with orthonormal eigenstates, right? Where again, R is the degeneracy of eigenvalue an. So, you know, there's a set of eigenvalues. They might have degeneracies. There might be multiple eigenvectors associated with that eigenvalue. But you can construct, you know, these orthonormal eigenvectors then. And, you know, and obviously for the Hermitian case, the an are real. Okay. Now, the interesting part comes is that there may be a continuous portion. There might also be continuous values. And these might overlap with the discrete ones, but typically speaking, they won't. There's a continuous spectrum, and we can denote that as A as a function of a continuous parameter. And here A acting on nu comma S. Now nu is a continuous parameter. It doesn't just have discrete values like 1, 2, 3. It can be a range of values. There might also be some degeneracy. Now we have the same kind of eigenvalue equation, but the inner product between two different vectors like this is no longer just these Kronecker delta functions. You get a direct delta function in the continuous parameter. And the degeneracies are typically going to be discrete, but they can also be continuous. And these guys are not in the Hilbert space, right? But these guys are in the Hilbert space. And in general, the operators will have, both discrete and a continuous spectrum. And a crucial feature of this is that if you ever try to dot the discrete eigenvector into one of the continuous ones, that they're obviously going to be mutually orthogonal. So that's always going to be the case. And finally, probably the most important piece of all this is, remember, completeness. Remember, back in finite dimensional land, we could always insert this identity, right? Where you sum over all the eigenvectors, you can insert this completeness identity. Well, you better hope that there's something like that for infinite dimensions, and there is. It just has a little bit of a different form. The completeness identity is a sum over both the discrete spectrum and including the degenerate, and it has a piece that comes from the continuous portion, which is now an integral over the continuous parameter, and it's these guys. That's an important formula. This is completeness. So you have to sum over the whole spectrum, both the continuous portion and the discrete portion. And look, this doesn't depend on whether or not A is bounded or unbounded. This is just the spectral decomposition theorem for any Hermitian operator. Oh, and of course, these guys are real. So the spectral decomposition theorem in infinite dimensions, it's just the same as the finite dimensional one, except you now have possibility for a continuous set of eigenvalues. You can be a continuous portion, like the position of a particle. You can measure, I can have continuous values. And the associated eigenvectors with those continuous values are called pseudoeigenvectors. And they're not in the Hilbert space, so you have to be very careful with them. But everything else kind of works. And, there's a generalization of the completeness relation. And the only other piece you have to add, this is the usual thing, and then you just have to add this piece for the continuous, the pseudo eigenvectors, and then everything else kind of works as you would in finite dimensions. You just have to use this for the inner product instead of the usual thing, 0 and 1. All right, any questions about that? Very important. So sometimes, operators like this include like the energy operator, the Hamiltonian. And if you ask, like, what's the energy levels of a system? Well, sometimes you like to, indicate them, right? And so there's always, there can be a discrete portion, which, you know, there'd be the ground state and so on. But for infinite dimensional Hilbert spaces, systems described by those, then there might be a portion where there's a whole spectrum, there's a whole range of energies that the system can be in. And that's the continuous portion of the spectrum, right? And these guys would be labeled by, you know, sensible states that are in the Hilbert space, but these guys will be corresponding to some continuous states which are not in our Hilbert space and satisfy a different orthonormality condition. You know, this one, right? Where these guys over here satisfy the usual one, like that. So it's good to think about it, sort of think about the difference there. Any questions? Sort of quiet. Does it make sense? No? Maybe?
Yeah, I mean, you know, like when you're talking about this continuous space, you know, that's what in the beginning of our class I was talking about, like, you know, quantum mechanics, we're measuring like the energy values in discrete values, right? But the energy value for E is actually continuous, you know. And I thought we were supposed to incorporate Riemannian sheets, and that way you can see that if we do a cut, it goes from the real values, like what we're calculating, to the imaginary, and then back, you know, to the next sheet and so forth. Isn't this kind of related to that in a way, if it's continuous, that there is, instead of like a discrete energy value there, like you're showing in that graph, that it is
Well,
actually using those sheets to kind of go from one energy value to the next?
sort of. You can imagine these Z. Remember, all this comes from looking at this operator. And this is an operator, right, where we're looking for singular values of Z. So you can think about them in the complex plane. You know, this is the imaginary part of Z, and this is the real part of Z. And so the eigenvalues of any operator, like the energy levels, they're going to be singular points in this complex plane. And, you know, and it's better to think about them as singular points of, you know, this operator. So when this, you know, when this is not defined, you'll have basically a 0 down here, 1/0. So those are like the poles of this operator function, and those would be, you know, some points in this complex plane. But you can also get continuous values of Z, and those you can sort of think about as kind of branch cuts in this complex Z plane.
So that,
you're familiar
so
with
now, like when I'm thinking branch cuts, like you just said, you know, they're like arbitrary. I can decide, as long as both the branch cuts that I make on each of the planes are the same, but I can make a branch cut anywhere. Is it the same for this too? It's arbitrary, you know, like I could say, this is how I was taught, at least in math methods. Well, and you know, you can just discretely take a branch cut and put it there, and then that way your discrete values you're showing would go into that imaginary part based on that branch.
Well, no, I don't. No, I'm not sure. So this is kind of not
Kind of
concrete
hard to
enough for me to be
explain.
sure. Yeah, I don't. You have to give me a particular example. I'm not sure. All I'm saying here is that Z is complex, and in principle, you know, the singular values, we can plot them on the complex plane, and there might be pieces that form a continuous set of singular values, which can live on a line, or they might, you know, they have different topologies. And then the discrete values, which would be like these regular eigenvalues, those you know, correspond to something that's effectively like a pole in the complex plane. The choice, I'm not sure that's quite right what you said about the branch cuts. I'll have to think about it. I mean, it depends on what, you have to give a concrete example. So I don't really. Yeah,
because that's what I was
you mean.
confused
You
about
can
when I
define a
heard.
function using a particular choice of branch cut, but once you make the choice, that's not arbitrary. I mean, that's just the choice.
Well, no, that's what I'm saying. What you can make a choice, though. That's what I'm saying. Then once you
Yeah, but
make that
it
choice,
has to be a more
then it's
concrete
not
example.
arbitrary.
I think I don't really think it's. I'm trying to say something much simpler. Just that
So, like,
when
because the
looking
way
for
I always
singular
taught it was the
values,
square
you
root
have
of
to look in the
x.
complex plane. What?
Yeah. Well, like for example, the square root of x, or I should say square root of 1, and you get plus and minus 1, right? And so actually it lives on 2 planes, right? And so the way he did it is he drew, like you said, an XY axis, and then you would have your branch cut, and then you'd have to put on the other XY axis the branch cut there, and it would just follow that circle. That's how he did it.
Yeah, sure, but that's not quite what we're talking about. I'm just talking about singular values of these operator valued functions.
Right.
So it's a little bit different. Okay. All right. Any questions though about the theorem in particular, spectral decomposition? You have to prove this. It's hard to prove that a Hermitian operator has this kind of structure. That's the hard part. And it's hard to prove this, this identity too, that you can write an identity on the whole Hilbert space as a sum of the continuous and discrete spectra. All right. But all right, so the other kind of operators we are interested in are the unitary ones. And remember, in infinite dimensional land, you don't know that the left inverse is the same as the right inverse. So you have to say that a unitary is, this is the full condition for the unitary. And U's are always bounded. Why? Because according to this definition, if you take U phi, right, then this is phi U dagger U phi, which is phi phi. So if you work backwards here, right, this has to be, so if you go backwards in logic, then you know that phi phi, a normalized vector, has norm 1, right? Then if you know that U dagger is equal to the identity, you can stick in the identity here, which you can interpret as U acting on the bra and the ket. So this always has to be bounded, so that means you can always act on phi. U acting on phi is going to give you something sensible that's in your Hilbert space. Never blows up, never does anything bad. And moreover, and you can use this spectral decomposition thing for a unitary operator. And a particular one we can consider is e to the I alpha times some Hermitian or self-adjoint operator. And the spectral decomposition theorem for this guy tells you that you might have some discrete portion of the spectrum which will have eigenvalues I alpha an, and then you might have some continuous portion d nu us of e to the I alpha a nu. So that's the diagonal version of the operator. And moreover, for these operators, you can take 2 values of this continuous parameter, and you can show using this that this is just equal to the product of the 2 guys. So it's got this transformation property that if you exponentiate this Hermitian operator, you get this unitary where the product of 2 different values of this continuous parameter alpha is just the sum of the 2 values. Again, this is just some real number. And we'll see these unitaries are very useful because they give you a connection between any Hermitian operator and any unitary. But Hermitian and unitary operators are related, as we'll see, via symmetries. And there's also a converse of this idea, is that any Hermitian operator, or rather, a converse is if you have a unitary such that, you know, it depends on some continuous parameter, such that this is the case, that if you take the product of two of these guys with two different values of the continuous parameter, it's equal to the sum, then there exists, and this is called the Stone theorem, then there exists a Hermitian T such that U of alpha is equal to E to the I alpha T. Important theorem. And you can actually prove it. And again, this is true in either finite or infinite dimensions, but it's an important aspect of unitary operators that they have a connection to a Hermitian operator. In many cases that we'll study. So it's good to look at, and we'll see this will be important for position and momenta, as we'll see. So let's look at, let's try to prove this. So suppose we had a relationship like this, right? Then what I could do is I can look at U at alpha plus a little bit. And that is gonna, you know, be equal to, according to this theorem, or according to the assumptions of the theorem, the product of these two guys. But if this is small, I can do a Taylor series expansion. You should be familiar with this kind of thing from the homework. Actually, you know, okay, so get U alpha, and now you have, you know, the identity Taylor series here plus the little bit delta alpha, and this is du d alpha evaluated at alpha equals 0. That's just the Taylor series plus, you know, higher order terms. And so we can take as a guess for what our Hermitian operator is, we can take T is equal to minus I du d alpha evaluated at alpha equals 0. And we can check that it's Hermitian because we can look at the following thing, right? We can look at U delta alpha, U dagger delta alpha. That, again, Taylor series expanding, that's the identity plus I delta alpha T, right? Because if I stick in T here, that minus I and I cancels, and you'll just get back this. But when you take the dagger, you'll get a minus I delta alpha T. And all of this, you know, if delta alpha is small, we drop the, you know, the higher order terms, and you get the identity, and you get a plus I delta alpha times, oh, and this is a dagger. Sorry, so yeah, you take the dagger over here, so you have to put the dagger on the T. You get T minus T dagger, and all of that is supposed to be equal to the identity because this is unitary. So the only way that's possible is if over here we have that T minus T dagger is equal to 0. So, so it's Hermitian. What else is just from this definition, right? We must also have that this definition and this guy. We must also have that du d alpha must be equal to IT U alpha. And so U alpha, if we solve this differential equation, must be equal to U at 0, e to the I alpha t, which is e to the I alpha t, because U at 0 is just 1, is just the identity. This is much like the time evolution operator. It's a general thing. So again, it's important to keep in mind in quantum mechanics, unitaries are related to Hermitian operators. We already saw this a little bit before when we did time evolution, in that the time evolution operator, this guy, was related to the h of t, the Hamiltonian operator, which is Hermitian, through an exponential. And this is a general rule, and it'll be important when we deal with position and momentum, which is, I guess, we're going to have to leave it for next time. But the next thing we're going to jump into is chapter 9, which is wave mechanics. And we're going to focus on the space L2R. And the operators of interest that we'll be studying, of course, are going to be position and momentum. These are going to be Hermitian operators, they're observables. And we're going to think about, states of our system that are maybe localized particles at some position x naught, so that when we calculate the expectation value of, say, the x operator, we get back, just x naught, and so forth. And that's, I guess, since I'm out of time, that's where we're going to start, and we're going to think about these two operators using all of these results from infinite dimensional Hilbert spaces, the idea that we have a continuous portion of the spectrum and this new way of talking about orthonormality in terms of the Dirac delta function. And also this property that any unitary operator will be related to a Hermitian operator. And we'll see that that gives us some idea of what the position and momentum operators do. We'll see that we'll be able to construct a unitary, out of position and momentum, which are Hermitian, by exponentiating them and seeing what that comes out. And that'll lead us to the canonical commutation relation, which is sort of always sort of given, but not necessarily told why this is a sensible thing to write down. We'll talk about this next time, where it comes from and how it's connected to these ideas about unitary operators and infinite dimensional Hilbert space, the spectral decomposition theorem. So we'll talk about that next time, I guess. Any questions? Anything else? There's still time to do the quiz, 10 more minutes, I guess. But yeah, any thoughts, comments? Again, this seems a little bit, the unitary bit, I just wanted to tell you, again, the spectral decomposition theorem works just the same way, except instead of real values, you get complex phases, right? E to the I alpha. So you get this kind of thing. And then in red here, I just wanted to tell you about the Stone theorem that says that if you have a unitary, it depends on a continuous parameter and satisfies this group property, as it's called. This is, how it works for time evolution. Then there's always a Hermitian operator T, which you can write the U in terms of that T as exponentiated like this. And this will be important. You don't maybe not see right now why it's important, but we'll use this theorem next time to talk about position and momentum, which, are Hermitian operators that live on an infinite dimensional Hilbert space, or they act on an infinite dimensional Hilbert space, which is the space of wave functions, L2R.
Right. Now, in our homework, question number 6, it kind of asked what you were saying about the